So, usually when we conceptualize catching a computer virus, right, we kind of fall back on this very linear, almost physical mental model.
Yeah, like a bad actor trying to cross a perimeter with a known weapon.
Exactly. You click a bad link, a malicious executable tries to download, and then your security system, compares that file against a list of known threats, flags it, and blocks it.
Right, it's very straightforward.
Yeah, and we like this model because it's tangible. I mean, it treats cybersecurity basically like border control.
It is a comforting paradigm.
Mm.
But looking at the threat intelligence reports and the zero-day disclosures from late July 2026.
Which is what we're doing today.
Right. Looking at that border control model is just fundamentally obsolete now. We are moving completely away from attackers brute forcing their way in with recognizable malware.
It's totally shifting.
Yeah, we're moving towards structural manipulation.
Yeah.
And they are weaponizing the perfectly normal, legitimate functions of a system directly against itself.
Which brings us to our focus today. Welcome to the deep dive, everyone. Today, we are analyzing a stack of recent cybersecurity firm research and threat intelligence reports to figure out exactly how this structural manipulation works in practice.
And we've got some really wild examples today.
We do. We are looking at 3 distinct cutting-edge threats. So there's a malvertising campaign that builds its payload dynamically inside a user's browser, a zero-day vulnerability in a foundational Java library that currently has literally no patch.
That one is incredibly concerning.
Yeah, super concerning. And finally, an Active Directory exploit that just hands over entire network supremacy by, manipulating legacy default settings.
Right, so the mission today is to dissect the mechanics of these attacks, like how and why they bypass traditional defenses.
So you can approach your own infrastructure with a 2026 mindset. It's about auditing the entire architecture rather than just playing whack-a-mole and plugging individual holes.
Because if you're relying on symptoms, like a known file hash or a government alert, you are already too late. I mean, the architecture itself is the vulnerability now.
Yeah, I've been thinking about a way to visualize this shift for anyone managing these systems because the old model, like we said, was building a taller wall to keep a burglar out, right? Or like checking their bag for a crowbar at the gate.
Right.
But the new threat model, it's like the burglar mailing you the individual pieces of a lockpick, entirely disassembled and disguised as office supplies.
Oh, that's a good way to put it.
Yeah, and they include a set of instructions, and they basically trick your own internal security guards into assembling that lockpick and unlocking the front door from the inside.
Exactly, because the pieces themselves aren't malicious until your own architecture executes those assembly instructions.
Right. So let's look at how that assembly actually happens at the perimeter, where the user interacts with the web. Confiant recently published this research on a malvertising operation they are calling sour trade.
Yeah, sour trade. It's been active since late 2024, and they are heavily targeting retail traders and cryptocurrency investors across, I think, 12 different countries.
In a bunch of different languages too, right?
Over 25 languages. They spoof trusted services, so TradingView, Solana, Luno. But here's the catch. They don't just serve malware to anyone who clicks the link.
No, they're much smarter than that.
Right. The landing pages employ really aggressive fingerprinting. If the incoming connection looks like, say, a security bot or an automated scanner, or a research environment.
Which is what defenders use to find this stuff.
Exactly. If it detects that, the server just returns a blank page or entirely benign content. The trap only springs if the visitor's browser profile matches a high-value target.
And when it does spring, it doesn't just point the browser to a static URL to download a malicious executable, right?
Yeah.
Because that would be too loud.
Yeah, that would immediately trigger conventional network defenses. Instead, it relies on the browser's own background functionality. It basically registers a service worker and builds a shared worker using embedded JavaScript.
Which, just to clarify for everyone, service workers are entirely standard.
Oh, absolutely. Developers use them legally and constantly. To manage background syncs, push notifications, offline caching, all that normal web stuff.
Right.
But sour trade hijacks this standard mechanism. The malicious page uses a config response that supplies a template, some session-specific random values, and a link to a secondary URL.
But this is the crazy part. That secondary URL doesn't even host malware.
No, it fetches a completely clean, legitimate developer tool called the Bun runtime.
Bun, like B-U-N.
Yeah, Bun is a highly performant JavaScript runtime. It's used by millions of developers completely legitimately. So the victim's browser retrieves and decompresses this clean runtime.
Okay, so it's got the clean runtime. What next?
Then the service worker fetches attacker-controlled portable executable or PE material alongside some JavaScript core bytecode.
So the browser's basically acting as a local manufacturing plant at this point.
That's exactly what it is. The worker script generates a pseudorandom byte stream, follows the attacker's template like a recipe, and just stitches the bun runtime, the PE material, and the bytecode together.
Into a single functional Windows executable file.
Right there in the victim's memory.
Wow. I mean, the implications for traditional antivirus are just severe here because the worker script uses a pseudorandom stream to assemble the components, right? So the resulting executable is mathematically unique for every single victim.
Yes, if you are relying on a SHA-256 file hash to detect malware,
Right.
you're completely blind. I mean, there is no central bad file signature to flag because the file literally didn't exist until the victim's browser manufactured it.
It's like trying to ban a specific type of poison cake, but the attacker just ships raw flour, sugar, and an oven right to the victim's kitchen.
Exactly, and it bypasses the mark of the web, too.
Wait, really? How? Because Windows usually applies that MOTW tag to files downloaded from the internet, to enforce Smart Screen and other security checks.
Right, but SourTrade launders the origin. Once the browser finishes assembling the executable, it passes the data back to the service worker as a readable stream.
Okay.
The service worker then hands it to the user through a hidden iframe using a specific content disposition attachment header.
Oh, wow. So as far as the Windows operating system is concerned.
As far as Windows knows, the file didn't come from the shady secondary domains hosting the PE material. The mark of the web record falsely identifies the trusted, spoofed landing page as the sole download source.
That is wild. So if there is no software patch to stop a browser from executing standard JavaScript, and like we said, file hashes are useless against dynamically generated executables, how does a defender actually stop this?
Well, defenders have to monitor the assembly line, not the loading dock.
Right.
You have to implement behavioral monitoring that flags strange service worker registrations or unusual configuration responses fetching, anomalous data streams.
Or hidden iframes trying to pass locally generated blobs as downloads.
Exactly. It requires inspecting the entire chain of behavior rather than waiting for a recognizable finished product.
So that's SourTrade, which weaponizes the client side using legitimate tools. But the threat model gets exponentially worse when the vulnerability isn't targeting a single user's browser, but is instead baked into the foundational code of a company's main servers.
Yeah, that brings us to the server-side analysis. Specifically, this critical flaw in Alibaba's Fastjson library. It's tracked as CVE 2026-16723.
And Fastjson is an incredibly ubiquitous JSON parsing library for Java. I mean, it is embedded in countless enterprise applications.
Everywhere. And this specific vulnerability carries an Alibaba-assigned CVSS score of 9.0.
Which is massive.
It's huge. It allows for remote code execution without any authentication at all. An attacker just sends a specially crafted JSON payload, and the server executes it with the full privileges of the underlying Java process.
So let's talk about the technical conditions for this exploit because they are broad enough to be really alarming. It affects Fastjson versions 1.2.68 all the way through 1.2.83.
Yeah, and the specific environment requires a Spring Boot executable FATJR running on JDK 8, 11, 17, or 21.
Let's break down why that specific environment matters for a second. Why does this require a FATJR rather than a standard deployment?
So a FATJR, or an UberJR, basically bundles a Java application together with all of its required dependencies and libraries into one single archive file.
Which is incredibly convenient for deployment, right?
Oh, developers love it.
Yeah.
But from an attacker's perspective, a FATJAR presents this massive, predictable surface area.
Because everything is packed in there together.
Right. When the malicious JSON payload forces the application to deserialize data unexpectedly, the attacker suddenly has immediate access to every single library bundled inside that FATJR. They can just use them as stepping stones for the exploit.
And this flaw bypasses the usual roadblocks we see with Fastjson exploits too. Like, historically, Fastjson vulnerabilities required autotype to be enabled.
Which allows the JSON data to specify exactly which Java class it should be deserialized into.
Which is obviously super dangerous, so most people disable it by default.
Exactly. But this new vulnerability, it does not require autotype. It functions perfectly, even when autotype is completely disabled.
Wow.
Furthermore, it doesn't even require a specific class path gadget, which is a known, exploitable chain of code pre-existing in the environment. It achieves execution without the prerequisites that usually constrain these Fastjson attacks.
And people are already using this, right? Threatbook and Imperva are capturing in the wild exploitation of this vulnerability right now.
Yeah, they are seeing active campaigns targeting financial services, healthcare, and retail infrastructure, primarily in the U.S.
And yet, and this is the craziest part to me, as of yesterday, July 25, 2026, Alibaba has no fixed version for Fastjson 1.x. There is literally no patch available.
None. The lack of a patch for a CVSS 9.0 vulnerability in a library this ubiquitous is just a severe systemic failure. Organizations are entirely exposed right now.
It's like having a building receptionist who automatically executes any instruction handed to them in an envelope without ever checking the ID of the person who dropped it off. And building management just refuses to change the policy.
That's exactly it. And adding to the chaos, CISA's recent assessment marked the exploitation status as none.
Which is just wrong based on the threat intel.
Right. It is completely missing from CISA's known exploited vulnerabilities catalog. So if you are an IT admin listening to this right now, and you're relying on CISA alerts to prioritize your defensive efforts for the week, you are currently flying blind to a massive unpatched threat.
So what do? How panicked should an IT admin be right now if there's no patch and the government hasn't even warned them?
Well, it highlights the danger of relying on patching in government catalogs as your primary security strategy. When a zero-day drops and the vendor fails to provide a fix, you cannot simply wait. You have to assume the malicious payload will successfully reach the library.
Our sources indicate the only immediate mitigation is manually forcing a safe mode configuration via a command line flag.
Right, the -json.parser.safe mode true flag. Or attempting to migrate to a highly specific non-auto-type branch of the dependency.
But those are just stopgaps, really.
Yeah, they are. The long-term mitigation, much like with SourTrade, is behavioral monitoring at the server level. You have to monitor the application for suspicious at-type values embedded within incoming JSON payloads.
You need to look for nested jar URLs being cutting unexpectedly.
Most importantly, you have to monitor the underlying server infrastructure for unusual child processes spawning from the Java application or unexpected outbound network connections.
Or the sudden creation of web shells. You basically have to catch the system acting erratically after the payload has been processed.
Exactly.
Okay, so we've examined the client side with browsers and the application server side with Java. Let's move to the identity infrastructure. Because the ultimate prize in any network intrusion isn't a single application server, right? It's the directory that governs access to everything.
Right. Active Directory, the central authority for authentication and authorization in a Windows environment.
So researchers 80J3N and Anik Fakhrul recently published a working exploit they codenamed Certighost. It's tracked as CVE 2026-54121, and it carries an 8.8 CVSS score.
And the impact is absolute. I mean, a standard low-privileged Active Directory user account can obtain a digital certificate that basically allows them to impersonate a full domain controller.
Which is game over.
Totally game over. Once an attacker holds a certificate validating them as a domain controller, they can initiate a DC sync attack. They simply request the directory replication data from the actual domain controllers, which includes the CareBTGT account hash.
And that hash is essentially the master key to the kingdom, right? For the Kerberos authentication system.
Exactly. With it, the attacker can forge golden tickets and access any resource on the entire network indefinitely.
But wait, gaining domain controller privileges from a standard, mailroom level user account? That shouldn't be possible without a massive complex code execution flaw.
You would think.
Yeah.
But Certighost isn't a memory corruption bug. It exploits the legacy structural defaults of Active Directory itself.
This goes back to what we were saying at the beginning. Weaponizing the system's normal rules.
Right. The entire exploit chain hinges on a default setting called machine account quota. By default, this is set to 10.
Meaning?
It allows any standard unprivileged user to add up to 10 new computer accounts to the domain.
Why is that even a default?
Well, it was designed decades ago to reduce the administrative burden on IT departments when provisioning new workstations.
Ah, okay. So how do attackers leverage that quota?
They use it to create a rogue computer account on the domain. Then, they run rogue LSA and LEAP services on that machine. They use those rogue services to intercept and relay an authentication challenge from the network certificate authority over the NetLogin protocol.
And the CA is the thing responsible for issuing those highly privileged digital certificates.
Exactly. The attacker needs the CA to look at their rogue computer account and issue a certificate meant for a domain controller.
So how do they trick the CA into doing that?
To force that misclassification, the attacker injects specific CDC and RMD values into the certificate request. These values act as forged metadata.
Okay, so the attacker is basically supplying their own parameters detailing the client and requester machine details.
Right, explicitly claiming the identity and structure of a domain controller. And the vulnerability lies in the certificate authority's validation logic. Instead of rigorously cross-referencing these supplied values against the authoritative hierarchy stored in Active Directory, the CA just blindly trusts the injected CDC and RMD parameters.
Oh, wow. It just takes their word for it.
Yeah, it processes the relayed netlogon challenge, accepts the forged metadata, and signs a domain controller identity into a certificate, handing it straight to the attacker.
It's like a mailroom clerk forging a CEO badge simply by shouting confusing instructions at the ID printer using all those injected values until it glitches out and just prints the badge.
That's a great analogy. And the researchers actually published an exploit that automates this entire chain.
Now, unlike Fastjson, Microsoft did patch this vulnerability recently, right? Like 10 days ago.
They did. They added validation checks to force the certificate authority to reject requests containing anomalous formatting, like IP literals, overlong names, or LDIP metacharacters within those metadata fields.
But, and this is a big but, the patch addresses the symptom, right? The CA blindly accepting manipulated input.
Exactly. It is vital to understand that the structural catalyst for this attack, the machine account quota default of 10, remains completely intact.
It's still there.
Still there. If administrators cannot apply the Microsoft patch immediately, their only recourse is to manually dive into the registry and disable the specific chase fallback routing paths the exploit relies on.
You know, comparing Certighost to Fastjson presents a really fascinating contradiction to me. Like, Fastjson has no patch, which is deeply concerning.
Yeah.
Certighost does have a patch, but the mechanics of the attack are arguably more insidious because they rely on features working exactly as designed.
I completely agree. The machine account quota isn't broken code. It's a legitimate configuration rule that was weaponized to dismantle the network's trust model.
It perfectly illustrates why default configurations in interconnected legacy systems are frequently more dangerous than unpatched software flaws.
Absolutely. The complexity of Active Directory creates these overlapping rule sets. Attackers simply map those rules and find the specific sequence of legitimate actions that result in catastrophic authorization failures.
So let's pull all of this together for a second. We started with Sourtrade, watching a browser being manipulated into assembling untraceable, mathematically unique malware from clean developer runtimes.
Right.
Then we examined Fastjson, a ubiquitous server library, blindly executing unauthenticated commands with zero patches available.
Yeah.
And we finished with Certighost, where legacy convenience settings allow a standard user to forge metadata and steal the master keys to an entire enterprise network.
The through line is undeniable here. Defenders must assume the breach has already occurred or that the architecture itself will actively facilitate the compromise.
Right. So for anyone listening who is responsible for securing these environments, the main takeaway is that the era of simply installing the antivirus and applying the patch is over. You cannot rely on a checklist of file hashes and patch deployments anymore.
No, you have to audit the behavior of your systems. You have to know what a normal service worker execution looks like in your specific environment.
You have to baseline the child processes spawning from your Java applications.
And you have to actively hunt for rogue computer accounts, leveraging legacy quotas. Security is no longer about static defense. It is about continuous behavioral verification of the infrastructure itself.
Which leaves me with a final, I think, highly provocative thought for everyone to mull over. Today, we are analyzing human attackers manually finding these structural overlaps, right? Chaining a legitimate browser worker with an unpatched server flaw and a legacy directory default.
Human-driven, yes.
But if this is the reality of our architecture right now, what happens in the very near future when autonomous AI agents begin actively negotiating with these systems?
That is the inflection point the industry is currently hurtling toward.
Because if an autonomous agent can map an enterprise network's configurations, legacy defaults, and application dependencies in real time, I mean, it will find these paths of least resistance faster than any human researcher ever could.
Oh, absolutely. It won't wait for a known vulnerability. It will simply test the logic of the architecture until it finds a sequence of legitimate operations that grant it access.
Right. So will the very concept of waiting for a vendor to write a patch become entirely obsolete when the attacks are structurally unique, dynamically generated, and executed in milliseconds?
It's a terrifying thought.
The threat isn't just someone picking the lock anymore. It's a system capable of autonomously inventing a completely new key based on the microscopic flaws in your specific deadbolt before you even realize you're under attack.
Something to heavily consider the next time you are auditing your default configurations.
Definitely. Thanks for joining us on this deep dive. Catch you all next time.